Good morning in North America and good afternoon in Poland. We are starting this webinar, and we are very honored to have a very distinguished speaker. Dr. Laurence Rilett is a distinguished professor in the Department of Civil and Environmental Engineering at Auburn University, and he is also director of the Auburn University Transportation Research Institute at Auburn University. Dr. Rilett is a graduate of University of Waterloo with PhD from Queen's University in Canada. He is an principal investigator on over 50 research projects with more than $60 million support for research. He received the awards from American Society of Civil Engineers and Transportation Research Board. Today, he will be talking about a very important topic of estimating and forecasting transportation metrics, lessons learned. Please, Dr. Rilett.
Thank you, Dr. Nowak. It's my pleasure to be here. I really appreciate the very honored to be part of this webinar series. I'm going to share my slides now. Dr. Nowak, just can you confirm that you can see my slides?
I see, and I hope everybody else can see too.
Yeah, we'll take that as a yes. That's great. So as Dr. Nowak said, I'm going to talk about a topic that I've worked on my entire career, which is simulation for estimating and forecasting transportation system metrics. By way of background, I'm going to give a brief overview of what our institute does, but then I'm going to jump right into traffic microsimulation. I'm going to give two examples, one on calibration and one on travel time reliability. And my focus is really on lessons learned, things that we've learned over the years that may be of use to the people listening to this webinar. And then I'll provide some concluding remarks. So by way of background, the Auburn Transportation Research Institute combines four groups: a highway research center, National Center for Asphalt Technology, GPS and Vehicle Dynamics Laboratory, and the Alabama Technical Assistance Program. They were all brought together 3 years ago. I'm the inaugural director, but it's just a very typical thing to do in the United States is to have these institutes that cross multiple departments and multiple colleges to get a very broad research, education, and outreach footprint. We're probably most famously known for our National Center for Asphalt Technology. It's a 1.8 mile, so about 2.7 kilometer test track for pavement, has accelerated testing. I'm gonna go to the next slide. So they put down pavement, different sections. They test different sections. They do it accelerated, so very heavy loads going around continuously. 5 trucks pulling 3 heavily loaded trailers, about 400 laps per day. And it's on a 3-year cycle. And right now we're in our 9th research cycle. And it's a way of testing out different pavement mixes under accelerated conditions to see if they have potential for use on the United States highway system. We're also pretty well known for our autonomous vehicle work through the GAV lab. As you can imagine, it's lots of different things, getting GPS, doing visual, doing LiDAR, fusing all that information together. The expertise here is on rural areas and under degraded environments. So what happens if you lose your GPS? Can you still do autonomous vehicles? We do have an autonomous Tiger racing team. You can see on the bottom right, I'm running the video right now. That's our our race car. It's going approximately 150 miles per hour. It's about 2 miles less than the record for autonomous vehicles, but they've been running this for a number of years now. All the software, all the technology was developed at Auburn by our students. And then lastly, what I do is looking at simulation. This is some work we're doing on simulation of everything. So the driver, the roadway. We want to get to the point where we can simulate the vehicle driver. We can do an AI driver. We can do complete environment, as well as the mechanical engineering of the vehicle. So that's sort of our overarching goal is, can we simulate all aspects of the transportation system? So theoretically, you could drive a system, a transportation system, whether it's a roadway or an arterial or a highway, before you even build it, and you can see what the issues could be. So lessons learned, we're a very broad institute. We have lots of challenges related to big data. We were interested in resiliency, reliability, and sustainability. So that's a very brief intro to our center, our institute. And now I'll go on to the main part of the talk, which is microsimulation models. Right here we have a microsimulation model that we developed, very standard one. This shows interstate highway. You can see the vehicles moving. You can do very sophisticated things. This model is a fairly old one, but it still shows the capacity of what you can and cannot do in terms of simulating traffic. And so a natural question on this is that the models have become very sophisticated, lots of parameters. And the question I want to ask on all this is, how do you know if this, is this a good model? Normally I'd ask everyone, get a response. My position, it's a good model, but only because I'm the one who developed it. So the real question is, how do we know something like this is actually replicating reality? Well, and the answer to that is model calibration. So model calibration, very simply put, I'm sure everyone's familiar with it. You have these default input parameter values in the model. We modify those so that the model accurately replicates the observed local traffic conditions. How do we do that accurately? We compare the simulated and observed data. And the question really is, what criteria and what statistical methods do you do? And that's going to be the focus for the next few slides. So how do we know whether it's a good model? How do we make it better? And just as a caveat on all of this, using the default values, just taking the simulation model and running it, it's usually a bad idea. It rarely replicates field conditions, and that's based on 30 years of experience. I've rarely had anything where I could just take a model and run it and be satisfied with the results. So what's a traffic simulation model? Well, you have supply input on one side. The supply, where are the roads, where are the bridges, how many lanes, how long are the links? The demand input is, where do people want to go start their trips? Where do they want to end? What types of vehicles are they? Are they cars? Are they trucks? Are they motorcycles? The simulation model basically takes that and gives you output, just as I showed on the previous slide. It models the supply and demand and says, this is how the system is operating. Now, you might run it once, you might run it, n times, and then average it, but you do get model output. And the question is, how do we know whether it's very good? Well, you could take the model output, travel times, and compare it to empirical data, travel times. So how good is it? Well, you do a comparison. What do you compare? Well, you could do statistical tests. You could test the mean. You could use t-tests, mean absolute error ratio. What's the percentage difference? I'll talk more about that. There's lots of ways of testing whether the data that you're getting from the model actually replicates what's in the field. Here's an example we did a few years ago. On the y-axis is average flow rate, vehicles per hour per lane. On the x-axis is station number or length. There's different places where we're collecting data on a highway. The observed data is this is this dotted line. The red line is the 95th percent confidence intervals from the observed data. So we're collecting data. We kind of know what the average volume flow rate is. We know the confidence on it. And then the dark line is the simulated data. And the question then is this a good model? And you might say, yeah, it's pretty good. It's within the 95th. So it's measuring, it's coming close to the observed. So I'm satisfied with it. However, you could also say, well, there are parts where it comes outside the 95th. So I want to make it better. You know, it's not exactly what I want. So that's up to the modeler, obviously. But this would be an example of how you compare simulated data with observed data. If you didn't like the model, if you said, oh, I don't like this model, how can I fix it? Well, if you're doing it by hand, you could say, well, I have my model output, my data. I could optimize it. I could change the model parameters and rerun it. And I could keep doing that until either I get a solution I like or I can't find a solution. There's no way to calibrate the model to the empirical data. And at some point, I'm going to stop. Okay? So calibration is just changing those parameters so when it models the supply and demand, the empirical and the model output are similar enough that the modeler is satisfied. So again, how would you test it? You could use mean absolute error ratio. I'll talk about that in a minute. You could do a t-test. There are others. A natural question is, why not just do every combination of all the model parameters? And the answer is, you could quickly show it's in the tens of millions. To even do a simple model will take you a long, long time to check all combinations. So that's even with our new computers and all of the things, it's almost impossible to do that in any reasonable amount of time. So calibration, what's the traditional measures of similarity? So I just picked, root mean square, mean absolute percentage error, mean absolute error ratio. They're all very similar. You take your simulated data, could be average travel time, could be your observed, you subtract off the observed number. So what was the observed travel time? What's the simulated divided by observed? Divide by the number of observations, and you sort of get an average percentage difference. The thing about these types of metrics, they're only valid if the distributions underlying them are identical. That's a pretty big assumption for traffic, and I'll show more about that in a bit. But we use it a lot. What's the average difference between the means? What if you're interested in the distribution rather than the central tendency? So instead of the mean, you want to know what's the distribution of travel times or speeds. We need that for reliability. We need it for sustainability. We need it for 85th design speed. In this case, what we're looking to look for is the closest of the observed and simulated distributions rather than just the mean. So rather than just worrying about central tendency or what's the average, we're interested in the entire distribution of the travel times. And I'll give an example in a few slides. Most statistical testing methods assume normality, but in transportation, we get a lot of bimodal or undefined distributions. We don't know what the distribution is. So in that case, there are non-normal modeling techniques, statistical techniques, Moses test, Wilcoxon test, KS test. There's a number of them. We tend to use these three a lot when we're not sure that the normality assumption holds, which is typically what we find. So let me give you an example. Here's a test bed from Houston, Texas. It's a major east-west arterial. It's about 1 kilometer long. There are 4 intersections, 3 signalized, 1 stop signs. It's part of the Houston Bus Priority Project, so we have a lot of data on it. So we went out, we collected travel time data in the AM peak, and you can see there's a large variability in travel time. The other thing to note that it's bimodal. The travel time is bimodal on this intersection, on this corridor. The reason's pretty straightforward. There are traffic signals. So the vehicles that have a short travel time, this one side on the left, they don't get stopped by a traffic signal. The ones on the right are getting a stop signal. So they're stopping, they're taking longer to go down the corridor. So we don't end up with a normal distribution, we end up with a bimodal distribution. So what we wanted to do is, could we the question is, could we simulate this, right? We could just run the model, right? Buy the software, run it once, call it a day. But we wanted to calibrate it. So we wanted to compare the empirical to the model. We wanted to optimize. We used the KS test and Wilcoxon test because it's not normal. And we set up a genetic algorithm to do this automatically. So you could do this by hand, but really you were talking tens of thousands of runs. So we want to run the model, look at the output, change the parameters, run it again, change it again. We want to choose the parameters in some intelligent manner. We use the genetic algorithm. There's lots of different ways of doing this. But basically, we're going to run until we get some answers, some optimization ones that are good, and then we're going to stop. Okay, so that's our process. What did we find? Well, here are the results. On the left axis is the mean absolute error ratio. On the x-axis is the p-value from the KS test. So essentially, anything blue is good. Anything orange is bad for the Wilcoxon or the KS test. Mean absolute error ratio, that's sort of the percentage difference. The lower, the better. If it was 0, they're exactly the same. Mean average, the average values of travel time are exactly the same. So what does this graph tell us? Well, the first thing, if we just use the default parameter set, we'd get about 20% error. That is actually very good for a simulation model. Usually, when you just run a simulation model without calibrating it, it's oftentimes 80%, 100% off on things like mean average values. When you look at the results, you can see that there's actually a large number of acceptable results that pass the statistical test. Okay? You can see all the dark blue ones, so that's good. Natural question is, how do you pick amongst them? That's a different question, but there are a number of parameter sets that actually give you statistically the same results as the empirical data. The acceptable mean average error ratio ranges from 0.7 to 6.7. So on average, the difference between the average travel time we measured and what we've simulated runs from about 7% and below for those values. And the other thing to notice that if you just did a calibration on average values, there's a large number that failed the statistical test, those orange circles. Okay, so what do I mean by that? I'll show that on the next slide. So here are two sets of results. These are travel time distributions. They have similar MAER values, so 1% off on the average travel time. But you can see that they have much different distributions. The one on the left is almost unimodal. It's bimodal, but it's very different than the empirical data. When you look at the one on the right, it's bimodal, and it actually follows the empirical data I showed earlier. And you can see that in the results. The one on the left was rejected. The one on the right was accepted. Okay? And you can look at it and go, yeah, you know what? My simulation model is giving me the same travel times I'm seeing on the system empirically. So what are the lessons? Well, I won't stress enough. Don't use the default values. I think most people understand that. You can calibrate models using new ITS, Intelligent Transportation System data. You can develop a statistically based calibration procedure. You can model bimodal travel time distributions. And it's important to calibrate to your application. In this case, we were very interested in the distribution. If we had calibrated to the average, we would not be able to analyze it the way we wanted to because we weren't calibrating to the distribution. So very straightforward. We have developed this over the years. Ours are all automatic. We run these fairly often. We've computerized them. So it's very straightforward to run the calibration models for different, this model happened to be VISSIM, but we could have used Paramix or any of the other microsimulation models. So that's one example of calibration and why it's important to calibrate. I want to talk about another one from the highway capacity model, reliability urban corridor. So what is travel time reliability? Well, the highway capacity manual, which we use extensively in the United States for our designs, defines reliability is the travel time reliability reflects the distribution of trip travel times over an extended period, right? So you see that word again, the distribution of trips, not the mean. It's a function of weather events, incidents, and work zones. And in the two latest highway capacity manuals, 6 and 7, they came up with a new travel time reliability estimation methodology for arterials. Fantastic. Here's a overview of it. It's fairly complicated. They take a base model, they get historical data, they adjust the conditions. Simply put, they run a Monte Carlo simulation. So they have a model and they run it over and over again, and they come up, and this is the key point, with the travel time distribution seen in the bottom right corner. So you can see number of trips, and you get a travel time distribution, right? Similar to the slides I showed before. So this is all estimation model, forecasting model that you can use it on existing roadways. You can also use it for roadways you're planning to build, okay? And from then you can get travel time performance, reliability performance metrics. For those of you familiar with it, planning time index, buffer index, just ways of measuring how reliable the system is, okay? I know I'm going through this fairly fast, but I think the key points are they have a method for developing the travel time distribution, and from that, they can do reliability estimations. We were very excited when this came out. We thought, oh, this is great. This will be really helpful for what we do. It was an important step. As I said, it estimates the distribution as well as the mean and variance, obviously. And from that, you can get reliability performance measures. The interesting thing about this process, this is the design guide for the United States. Nowhere in the literature did they talk about how they calibrated the model. Nowhere. So we thought, well, let's test it out. Let's test this model that they are telling us to use against empirical data, because right now we have lots of empirical data. I'm going to show you one example. So we're going to do travel time distributions on arterial road, and we want to compare this methodology with empirical data we measured. So what data do we have? We have a lot of low-cost archived Bluetooth data. So travel time data from one point to another. We want to compare the empirical Bluetooth data to the forecast HCM travel time on these corridors. The objective is improve forecast travel times distributions or reliability. So here's an example. You can see it's about an 8-mile section of corridor. This happens to be in Lincoln, Nebraska. It's about 12 kilometers long. It has a number of traffic signals along it. The blue lines are where our Bluetooth data is, so we have fairly good travel time information on this corridor. It has a fairly high ADT of about 30,000. For those of you who are familiar with level of service, it has ranges from B to D, so it's not completely congested, but it has high volumes. Okay, so lots of delays on this road during rush hour. So what did we find? Here's the Bluetooth travel time distribution. This is the empirical. This is what we measured. So on one side is the histogram, on the other is the cumulative distribution curve. You can see that the mean's about 65 seconds, standard deviation is about 11 seconds, okay, for this corridor. We then went and ran the highway capacity manual for the same period, and you can see it has a fairly similar mean. So the model is, arguably not bad at picking out the average distribution. But you can look at the standard deviation or the spread, and you can see it's much tighter than the empirical data. Okay, here's a comparison of the two. Again, the blue is the actual Bluetooth. The red is what the highway capacity manual is saying would happen on this road. Now, we can talk about all kinds of different statistical tests, but just looking at it, you can tell that the highway capacity manual is not replicating the empirical data at all, okay? Probably not surprising because they never calibrated the model, but again, we could not replicate that. So the HCM procedure, which is a simulation approach, underestimated the travel time variability and therefore underestimate the reliability of this corridor. So if you're using it to model reliability, it would be pretty wrong. From a user perspective, it's really problematic because the HCM indicates the corridor is much more reliable than the empirical data might suggest. And I should say, we're just showing you one, I'm just showing you one example. We did this across the country, across different arterials, thinking that we were doing something wrong, but actually at no point did we find one that worked in terms of measuring the empirical, right? And you can see it. On the red, that's the HCM, very tight, looks very reliable. The blue is what's actually happening. You could argue not very reliable, lots of variability. So the next question that came up was, well, could we calibrate? We talked about how we calibrate things. Could we calibrate the model? We have the empirical data, we have the output, we could change the model parameters within the HCM. Could we calibrate it? And the short answer is yes. The Bluetooth travel times are shown in blue. The HCM uncalibrated, so this is a cumulative density function. HCM uncalibrated was red. You can see they're well off. And when we calibrated it, you can see with the green, it came very close to the Bluetooth. So could we fix the model? Sure, we could fix it so that the HCM6 actually replicated what we were seeing. So we could calibrate it to the empirical data. So lessons learned, reliability, increasingly important, understanding the variability of travel times. There's a need to forecast travel time distributions as well as the mean and variance. And you really have to calibrate and validate to local conditions. That's our number one takeaway. We never came up with a calibration that worked across the United States. It was always, could we, in this city, these are the values that work for the empirical data. So in summary, traffic microsimulation models can be applied anywhere at a low cost. We're starting to see our manuals adopt these. So HCM6, as an example, is using Monte Carlo simulation. However, the whole focus on my talk is that the calibration step, skipping this is often a bad idea. In fact, it's a really bad idea. You should calibrate to your local conditions, right? So what we found is that you can't go in one city and then go to another city and assume that that calibrated model will work. And really, you need to focus on the specific application. If you're interested in distributions, you really need to calibrate to the distribution, not to the mean. And in closing, I've worked in this area a long time. I always love this quote from a famous statistician, Box. All models are wrong, some are useful. And I often take this when we're talking about simulation. Is the microsimulation model we're using useful for the application? Is it giving us the information we need to do the job? And the second question really is, have they been calibrated for the application and the location, right? If so, you could have a very, these models could be pretty useful to you. It's unlikely they're going to be 100% correct, but they could be very useful. If they haven't been calibrated, it's unlikely it's going to be useful because it's probably not going to measure or replicate what's in the field. And with that, I would thank you for listening to my webinar. I'm going to stop sharing, and I'll turn it back to you, Andy.
Thank you. Thank you very much. We would like to entertain some questions. I have questions prepared also, but I do not see the audience. So I do not see if anybody.
I think if they have questions, they need to put it into the chat, right? Because I think they're muted.
Okay.
But there's nothing in the chat, so.
Yeah, why don't you do that? And in the meantime, I may have some questions, and that is you are talking, the talk is processing of the data, traffic data. And we have a number of researchers at Polish universities interested in pavements and bridges, and what is the impact of the traffic on the bridges and pavements. Can your simulation results have some input in this area?
Yeah, that's a great question. Yeah, we've worked on this topic with our pavement and bridge partners for over 20 years. So the answer is yes. When you look at the simulation models, the one I showed, it shows trucks, right? It shows cars. You can get the output specifically by trucks. You can get it down to the vehicle. Where are they located? What's their speed? Are there trucks next to each other? Are they in the same lane? All of the things you could need to come up and calculate your ESOLs and then the demand on the bridge or the pavement. These simulation models can do that, and we have done that, right? And then if you have restrictions, the trucks can only be in the right lane, you can model that, right? The trucks are only in the right lane. What's the effect on the bridge? We can do that. The only thing I'll add is that these models were never developed or calibrated to model accurately the truck and cars, the behavior of them. So in that case, you really have to go through and do what I said, calibrate it. So if you're very interested in what's the spacing between the trucks, and you want to make sure it replicates what's going on in the field, you have to go out, collect that data, and then calibrate the simulation model to what you're seeing in the field, right? So is the trucks going over the bridge at 65 miles per hour or 90 kilometers an hour? Are they stopping on the bridge? All of those have impact on the bridge or on the pavement. And you have to make sure that the data you're getting from the simulation actually replicates what you're seeing in the field. Now, once you have that, once you've calibrated that, and that is not a simple step, once you've done that, you can then do all kinds of sensitivity analysis. What happens if the truck increased by 20% or 30%? We know how they behave. What happens when they get larger? Then you're allowed to do much more sophisticated analyses. The second thing, Andy, that I'll mention is that you talked about WIM data early on. So the weigh in motion data, you can actually connect that to it's very easy to connect the weigh in motion data to the trucks. So if you know the distribution of trucks and their weights, you can then connect that in the simulation and say, well, these trucks are heavier, they behave this way. These trucks are lighter, they behave this way. And you can actually get a pretty good representation of what's going on at a given location, a bridge, for example, that replicates your weigh in motion data, if that's what you want to do.
I think I see an application of what you are presenting in the area which is of great need, and that is simulation development of the load for long span structures, long span bridges, where the mix of the traffic presence in multi-lanes. The big bridges have often 4 traffic lanes in one direction, and how modeling, simulating such a traffic is a big problem. And I see that joining forces with transportation engineers can be very beneficial for both structural engineers and transportation community.
Right. And in the US, and I'm sure in Poland as well, we're forecasting the amount of freight traffic is not decreasing, it's increasing. And a lot of people are saying that in the next 20 years, we're expecting almost a doubling of the weights and the freight on our highways, on our major arterials. So obviously, if you're designing bridges and pavements for something out 10, 20 years, knowing that the traffic's going to increase is kind of critical as well. And if properly calibrated, these simulation models can help with that design. So instead of just saying, oh, we think traffic's going to be this much heavier on average, it's going to do this, you could actually model what that implies for different bridges if you have a simulation model you're confident in.
I still don't see other questions. I have a webinar chat opened and encourage you to ask questions. The next question I have is you are your presentation is very much dealing with the processing of large volume of data. What about the quality of the data? How do you filter the false information from the information which is correct? Sometimes the data may appear correct, and that is the most difficult and tricky part when there is no clear indication of problems.
Yep, that's a great question. So in the United States, and I'm sure in Europe as well, we've sort of flipped the environment in the sense that 20 years ago, 30 years ago, when I started off, data was very hard to come by. We'd have to go collect it ourselves. And as Dr. Nowak indicated, now we get terabytes of data. We collect all kinds of data every day. We can't even, it's hard to keep up with all the information we're getting. But the question is, what is the quality of that information? And I don't have time to go into this in this talk, but other than to say, we've looked at a lot of this data. In fact, we just had a paper on the quality of data, and we're finding even on these large databases that have been essentially cleaned and given to people from the US government, there are still major issues with them. We're finding errors, we're finding bias on these travel times and these volumes. And people were being told, these are what you need to use, but we're finding this. So to get to your question, Andy, which is a good one, yes, the data, they collect the data. How do you know if it's any good? Weigh in motion is a classic one where you have lots of weigh in motion data, but a lot of it is really bad for a variety of reasons. So what we do when we're talking about calibration, almost exclusively, we go out and collect our own data. And we make sure, so we can either compare that to the data we're being given, so we can confirm that the data we're being given actually is correct. And we do a lot of that. Or we just use our own data. Like in the example I gave, that was our data we collected. We were very specific on what we were collecting. And we had very good confidence in that, rather than just assuming something that's automatically collecting data is working for us. So it's a great question. What we found is collecting our own data, and particularly the data that fits the application we're interested in, right? So if it's weights, we have to go through and actually physically calculate to get the weight data and calibrate to that. That's fairly difficult. Travel times are a bit easier, but it's a great question. We get lots of data, but a lot of it we do not trust unless we're collecting it and confirming that it's correct. It's unfortunate, but that's just the way it is. And a lot of times the data you need is not available, right? So if, for example, if you're interested in trucks on bridges and you're interested in the spacing, that may not be available anywhere. You have to go collect that. If you want to know what the truck spacing is and the speeds on a bridge, you might have to go collect that yourselves to make sure the simulation model is being accurate.
Actually, we have this data. I mean, the weigh in motion measurements with high frequency of reading, like 200 readings per second.
Right. I guess what I'm saying is we have these automatic detectors, right? We count cars, we count speeds, we count weights. A lot of them have huge accuracy and inaccuracy. You can see them. They're like, 20% of your trucks are, they're just not measuring correctly is all. So the bad ones you can pull out. Oh, that's clear. A speed of 200 miles per hour or a negative speed, that doesn't happen. So you can pull those out. But your point is, what happens if they're close? Yes, we collect a lot of automatic stuff. I guess what I'm saying is we rarely trust the automatic stuff without validating it first to make sure that, because all those automatic ones have to be calibrated, right? Someone has to go through and calibrate them, often run by state DOTs or, often a lot of them who don't have a lot of money to go out and calibrate, make sure that the detectors are working. They're much more interested in this data coming back, but they're rarely interested in, is that data correct, if that makes sense? Because for them, it's not the same use, right? They don't need it to the accuracy we need it for. And so it's not a criticism of the state DOT. It's just they're collecting it for one use. We need a different use. We probably need it more accurate, a higher accuracy. Does that answer your question?
I think it does.
Great.
I am still looking for the questions from the audience. And the next item, which I would like you to elaborate more on, is transportation reliability. This is the reliability. Everybody's talking about data which is reliable, the transportation system that is reliable. There are some other words which we are using: resilience, sustainability, but let's focus on reliability. What would you add to what you already presented?
Sure. No, I think it's a great question, because all those, resilience, sustainability, they're all very similar, answering different, questions about the same system, transportation system, in slightly different ways. What I talked about in reliability, and I know you're an expert in structural reliability, the reliability I was referring to, and the one that has probably the most interest now, is travel time reliability under normal conditions, right? So how long does it take me to go from point A to point B? So I could tell you, well, it's average, it's 20 minutes. But a user might be interested in, well, I don't care what the average is. What's the longest it's going to take me? Is it going to 24 minutes? I have to be somewhere. I want to leave 24 minutes ahead to make sure I get there. That's the reliability. And that's why the distribution of travel times becomes very important. So we're not just interested in the average conditions. We're interested in the variance around those conditions. And then reliability, as you know, is really a relationship between the mean and the variance, right? I could tell you that there's a standard deviation of 10 minutes. That means one thing for an average travel time of 10 minutes. It means something different for an average travel time of 60 minutes, right? One is very reliable, the other is not very reliable. So that's sort of the holy grail, is how do we go and measure this reliability on these individual links, these corridors, and then how do you then convert it to a whole system? What does it mean to have your whole traffic system or interstate system be reliable? So that's under, normal conditions. And then, as you know, the next one is, what about abnormal conditions? What happens if there's, a tornado or a hurricane or a fire or an earthquake that takes out part of your system? How reliable is that system is a different question, but it's very much the same in terms of what's my average conditions, what's the variance. And there's a direct correlation, obviously, Andy, to your work on structural reliability. Different application, but the statistical concepts are the same.
There is one thing which we are facing often with processing the data, the size of the data. This is really big data. But we are not equally interested in that whole volume of data. We are interested in the data which is critical, and that reduces the computational effort, that makes it more focused. I wonder if in transportation you are also facing these problems. I'll give examples from our area and see how it relates to transportation issues. If we're interested in strength of material, our interest is on the low side of the values. We're not interested what percentage of our material is stronger than what is required. We're interested what percentage is below. We are not interested in trucks which are very light and do not contribute to fatigue of material, but we're interested on the higher side. If you focus on these groups of data, then it requires less computational effort. and is easier to consider.
Mhm.
How do you approach that in the transportation area?
Yeah, that's a great point. Yeah, and obviously, when we talk about pavements and bridges, we don't really care about the car weight because the impact is so much less. It's sort of round off compared to the truck weights. Yeah, I think from our perspective, yeah, we do worry about things when we're talking in transportation about 95th percent. What's the 95th percentile? That's why the distribution was sort of important on what we're dealing with and why I talked about it. So it's hard to do a distribution without knowing what the fifth is. The other reason it's important to consider everything and not just some is that, yeah, we may say we're interested in the trucks. Like I'm only interested in the heavy trucks. So tell me what the effect on the bridge is from your simulation model. Well, we can do that, but the reality is the cars interfere with the trucks and the trucks interfere with the cars. So, for example, United States, the big trucks tend to be limited in speed. It's about 67, 68 miles per hour. In the West and the South, a lot of the speed limits are 70, 75 miles per hour. So the cars are going a lot faster than the trucks and they're interfering with each other. One truck passes another, it causes traffic jams. So even though we may be interested in the trucks, trying to do the truck analysis without understanding the car behavior and how they interact is very difficult. So yeah, I agree with you. A lot of times when we're doing the pavement and bridge stuff, we're interested in the trucks, but it's almost impossible to ignore them without the cars. So we
Great,
tend
great,
to
great.
want to know, information on trucks and the cars. And again, a lot of times you have to collect that yourself.
So the model is with space occupied by vehicles, and that's one variable. And then the actual weight of these vehicles uh, with occupying a certain space, that's
Right.
another one.
And the holy grail, of course, ideally what you love to do is take all that weight in motion and say, this truck we're simulating is a very heavy truck. So if you're going up a steep slope, it cannot go very fast. Whereas this one is unloaded, it has different things. We're not there yet, as far as I know, that we can get to that level, except at the very simplest analysis, maybe one bridge. But that sort of would be grand to be able to do that, is have the vehicles have all these different characteristics that replicate what goes on, right? Because obviously when you're in the mountains, the trucks behave much differently than when you're on flat ground.
Uh, and now I would like to ask you a question which I think would be of interest to our colleagues in Polish universities, and that is uh, what are the gaps in knowledge in the area which you presented, which are of need and interest, uh, and that may be a potential basis for collaboration.
Yeah,
That would be our center, Poland in Silicon Valley.
that's a great question. I think
Is supporting, that research, and I'm sure that our colleagues are working already in transportation would like to know whether what they are doing is of interest, and are there American potential partners interested in such a collaboration?
Yeah, that's a great question. So yeah, I think I showed some of the autonomy vehicles we're doing. I mean, that's sort of the hot topic right now, is getting information and running it in a smarter way. In terms of simulation, which is what I was talking about today, you know, what I wanted to get across was the simulation models are very sophisticated and it's very easy to take them and run them and get answers. But we really have to be careful that whether those answers are the correct ones or not, right? Is it a useful model or not? In terms of your question on what the modeling, what's the next step in modeling, I sort of talked about it right at the very beginning, but I'll reiterate it now. I think where we're going to get to is where we can take actual drivers, and we've done this a bit, but it's still in its infancy, is take actual drivers, human drivers, and put them into the simulation. Make sure that the vehicles themselves are actually modeling the vehicle correctly. this is an electric vehicle, has this characteristics. This is a internal combustion engine, with a fairly small horsepower, has this characteristic. This is a truck heavily loaded. So getting the trucks correct, the cars correct, getting the drivers correct, whether it's an in-person vehicle or an AI driver following it, and then having the roadway connect, right? So essentially getting all three components of the system, the driver, the vehicle, and the infrastructure, all highly accurate, all connected correctly so that the results are more closely related to the reality. That's what we're working on right now, and that's what sort of excites me over the next 10 years, is being able to get to that point. We're very good on simulation, but a lot of the stuff is very approximate, and I think we have the opportunity to make it, with the more computers and the more data, as you indicated, we have a much better chance of getting really strong simulations done if we do it correctly. So I would love to talk to people, but I'd be happy to talk to anyone about collaborating on those types of ideas that we're sort of working on now.
And of course, you see the need to keep collecting the data because that is, we know very well that traffic keeps changing. It's traffic in a few years down the road will not be the same. So even if we have a model which simulates well today's traffic, when we think ahead of time, and we are building transportation infrastructure to serve not tomorrow, but serve years ahead.
Yes, you're right. And so one of the things we do a lot of is we have test beds where we collect the data. And I told you it was in the chat. If the questions are actually in the Q&A. So Hamid pointed that out. So my mistake, Hamid. It's in the Q&A. So do you want to read the question, or you want me to?
I don't see them. Oh, I see now.
Yeah, it's Q&A.
Okay.
So it was my mistake.
Okay, I'm sorry. Okay. The question is, traffic inside cities and urban centers seems to behave different to traffic in the interstates or rural roads. Can the model structure itself account for that? If not, what do you do to account for that?
Right. That's a great question. And the short answer is yes. So where it comes in is obviously the vehicle characteristics aren't going to change. If you're a truck, you have certain characteristics, go up a hill. That part of the simulation models does not change. So assuming those are correct, whether you're in a rural environment or whether you're in an urban environment, the vehicle should behave the same if it's calibrated correctly. Where the question really comes in is you're saying, is the drivers behave differently, right? Because the environment's different. In an urban area, you might have lots of vehicles around you. You can't switch lanes. In a rural environment, you can go faster speeds because there's not as much. You can pass vehicles. So the answer is yes. The models can handle that. The only caveat, the only thing I would say to keep in mind is that, again, getting it calibrated is critical. You have to have information on how the drivers behave in a rural environment, and then calibrate the model so the drivers in the simulation replicate what the drivers in the rural area will be doing. So you can imagine if I calibrated a model in an urban city, and then I just took that model and said, oh, it'll work out in the rural area, the odds of that being true are about zero because you never calibrated to behavior in a rural area. So great question. The answer is yes, the models can handle it, but it goes back to what I said earlier. I would strongly recommend people calibrate to the application they're doing. If they're doing a rural application and they're interested in passing, they need to collect data on that and calibrate the simulation model to replicate the empirical data they're getting. And at that point, they can then have some comfort in doing sensitivity analysis. What happens if we have more traffic or different volume, different grades, those types of things. So great question.
We have one more question. Very interesting lecture. I have a question related with different forecast travel time distribution. Is it possible to use conditional value at risk and value at risk instead of mean and variance?
Yeah, another great question. The answer is yes. But in the US, at least, we're very happy to have gone from, I'm saying my whole career was very much, here's the average, here's the average, here's the average. It's only in the last 10 to 15 years in practice, we started to talk about not only the mean, but the spread, right? So mean and variance. I'm a big proponent of just using the distribution, and then everything you've just said, you could use the distribution in any way that you're comfortable with. As Dr. Nowak said, oftentimes we're interested in the extreme values, and that to me makes sense. So yes, the answer is yes. What we tend to do, and this is a subject for some other webinar or some other discussion, is they tend to come up with new metrics for reliability. So they're just not happy with the distribution. They come up with buffer index. They come up with just, travel time index. They come up with these indices. A lot of times they don't make a lot of sense. In fact, a lot of times they're wrong. So in one sense, we're very happy we're moving to reliability. We're very happy we're moving to mean and variance because that's the first step. These other ones are being researched, and we're part of that. And I look forward to developing even new ones. But again, it's a challenge. We're just getting people to the point where we're talking about reliability, so we're happy with that. But the short answer to your question is yes.
I would add and ask you to comment on this. Fitting the actual data to one of the common distributions is often misleading and wrong. I mean, the lower tail of the distribution is often very different than upper tail of the distribution. So depending which one is important, there is no point to force that fitting. It is much more efficient, and the computational possibilities are now very different than they were 20, 30, 40 years ago when they tried to have three parameter distributions to fit the situation. We don't have to do that now. Do you agree?
Yes and no. So yes, as you saw, when I talked in my presentation, it was very much what's the distribution. I rarely said, oh, it has to fit this Gaussian log. In fact, rarely fit Gaussian, but log normal, chi, Weibull. Yeah, you don't have to fit it because we have so much data. We have the distribution, and if there's something going on in the extreme value, they're kind of fat. You don't need to say, oh, we don't think it's a fat tail, right? You have a fat tail because it's empirical or it's simulated that way, right? So as long as you're confident in the results, whether empirical, there's not a lot you have to do. You can just calculate it directly. Where I would disagree is sometimes it's nice to get a simple model, rather than having all these parameters in the simulation. If you're giving out general guidelines, taking that data and fitting a model to it and saying, here's the three critical parameters, I don't have a problem with that as long as you understand, it's a simplification. It's a useful model, but that there's a reason for doing it. And we've done that in the past as well. But in general, I agree with you, Andy. Right now, there's no need to assume model. It goes back to what I said earlier. Before we had very little data, we'd fit a model to it and say it works. Now we have the opposite. We have so much data, we don't need to really fit these 3-parameter models through it. We know what it looks like because we have all this good data.
I think we ran out of time, 1 hour. So I would like to thank you very much for preparing this presentation and presenting it. And thank you, those who had questions. And I think you will probably accept questions if anybody would like to ask you So please go ahead and send your questions. If you don't have any other addresses, send it to the center, and the center will forward it to Dr. Rilett.
Yeah, should
So
be easy.
thank you all for participating. Thank you.
Great. Thank you. Take care.